Yeah, welcome to the web and mobile track. Our third speaker is Mr. Joshi, co-developer of stdlib, and his topic today, numeric and scientific computing inside your web browser. Right, let's welcome him. It's a 25-minute talk. Yeah.
Hey everyone, happy to see you all around here. So today I'll be talking about numeric and scientific computing inside your web browsers. So I am Gunj Joshi, a core contributor at stdlib. stdlib is a fundamental library for numeric computation on your web browsers, similar to like what we have NumPy or SciPy in Python. Let's get started. So first of all, I want to motivate why do we need to perform computations of any kind inside our web browsers. Basically, there are 4 key reasons for that. First one being instantly accessible. You don't need to install anything else when you are computing inside your web browser. So there are no external dependencies that you need to install. Just your web browser, your Chrome, your Safari, whatever you use, and that's enough. Second point comes out to be for privacy and security. So the data which you are using to compute anything stays inside the client's machine in your own device. So the data isn't being transferred to any undisclosed location where the server is located. So you have your full data privacy because the data never leaves the client's machine. Then comes the point of low latency. So as the computation is being performed on the client side, you don't have to face network issues, sending data over to the server, then it comes back. Latency becomes very low. Then you have a major point of accessibility. So client-side computation can be used to enhance the accessibility of your day-to-day web applications. So even if you have a low-end device, you can use web-based computation for some assistive technologies. The demos for some of those things we'll have later in this slide. Yeah, so I have some demos ready for you. So these demos will help you visualize what are the different fields in which web-based computation can help us. So first of them is a digit classifier. This is based on TensorFlow.js. So suppose we have a digit, we create it, and then it detects what we have drawn. Similarly, if we have we draw any number, it gives the probabilities of these digits. So it detects 7 as 1, but it works sometimes. After that, we have an toxicity detection. So sometimes what happens is, there are various social media platforms. You have multiple comments on any post. What if you can, detect which comment is toxic and which is safe? That can be also done on your web browser. No need to, send everything to the server. Such as, suppose someone says, this, and then we try to classify it, it detects it as true, so it is toxic. But if there's a normal thing, it says no, it's not toxic. So this is also one of the use case where we can leverage web-based computing. We also have multiple OCR features. You might have heard about OCR.space. So that what it does, when you upload an image, it sends the image to their servers, then they extract the text out of it, and then they send it back to your client, to the client's machine. We don't need servers for OCRs such as Tesseract.js. What they do is they also have the entire computation on your web browsers. So suppose we have a sample image here, they extract the text out of that image and display it here. This is entirely web-based. After that, you can also visualize training an entire ML model inside the web browsers. Yeah, you can do that as well. So this is a simple visualizer where you can visualize a model being trained without a server being involved. So we load the data here. We have some digits example from MNIST database. You might have heard about it. And then we can start training our model. So all this is happening on your web browser. So like the hardware of the client is getting used. We have some custom training charts, accuracy, confusion matrix, all those stuff. After that, some accessibility applications are also there where this comes of quite a good use, such as WebGazer. What we can do in this thing is, first we have to calibrate it. So what it does is, based on my eye movements, it tracks my eye movements and then it moves this red dot around the whole screen. First there's a process of calibration. We have to calibrate some of these points on the screen. And then once it is done, it is able to track your eye movements. So see, now wherever I take my eyeballs, it just moves the red thing also. One such more use case is HoloBooth. This is similar to WebGazer, but what it does, it instead of tracking only your eye movements, it tracks your entire face. So as I turn my head, this also moves. So these were some of the demos. Now let's go ahead with some distribution and communication of scientific results. So scientific computing is not only about computing and getting the results. It's also about how you share those results, how people from the whole community can get those results. So for that we had Nature plus Jupyter notebooks, traditionally what we were using, but those notebooks have some problems with them. The problems include those notebooks are not built for production. They need a backend. So what if we can achieve all that without a backend? We'll have a look at that as well. As they need a backend, their deployment requires special infrastructure. Hosting these Jupyter notebooks, it requires dedicated cloud containers and containerized environments, meaning those are expensive. And there are security risks as well. Arbitrary code can be run inside these Jupyter notebooks. What if someone runs RMRF or some malicious code? You're gone. Difficult version control. So as the Jupyter notebooks have JSON based format, so that makes tracking of version changes a bit difficult because the differences are a bit noisy and large. So in order to tackle all these challenges that we had been facing, we have some web based notebooks. So what these kind of notebooks does is that they do the entire computation inside your web browser. So they run entirely inside the client's machine. Web server is required only for deploying that websites, not for the actual computation. So those turns up in lower costs and faster accessibility. Here is an example for one such web-based notebook where we do real-time k-means clustering. Let's have a look at that. Yeah, so this is one such observable notebook. So this platform is observable. So through observable, you can run JavaScript code in these kind of notebooks. So let's see. Yeah, so we'll start the k-means clustering. Just uncomment this line of code and we'll just play it again. So you see, the clustering is happening directly inside your web browser. So no need of a server or a different computation environment. Your own machine is getting used over here. And this is all happening in the client's machine in real time. Now we're talking about scientific computing. So now let's break down what are the key ingredients that make web-based scientific computing possible. So the key ingredients include syntactical niceties. We should have some, syntactical sugar for web-based computing. One such example of that is R's pipeline operators. So instead of doing, first taking the square root, then mean, then some C function, you can just have a pipeline of operators, one of the features of R. After that, we have some site extensions as well. We just saw observable notebook, which is used to run JavaScript. So site extensions, what they help us to do is they help us to compile our code inside the web browsers. So observable for JavaScript, Jupyter for running Python, and there are a few more as well. Scientific computing ecosystems also require bindings to some hardware optimized libraries such as BLAS, which is basic linear algebra subprograms, or linear algebra pack, popularly known as LAPACs. So what they do is they use SIMD or vectorized operations to run the code at near native speed, again in web browsers. There are also some data structures tailored to numerical use cases, such as ND arrays. Most of you might be well aware of those. So what we are doing is we are importing NumPy, we are initializing the array, and we are getting the shape of the array. So those kind of specialized data structures, they help us in scientific computing ecosystems. One more such example is of data frames in pandas. So what we're doing here is also similar to, like, we're creating a 2D table with name and score fields, setting up with data, and then using it. One more important thing comes out to be for vectorization. So what vectorization is, suppose you have an array of data. There are many elements in an array. Now suppose you have to perform the same operation on each element of the array. Traditionally what you would do is, running a simple for loop and running the same operation on each data, each element. That happens without vectorization. We're just using a simple for loop here. But if we use vectorization, the whole array is processed at once. So there's no need of computing each element multiple times. We can have all that operation on the entire array at once. This is one such example of to understand vectorization better. So let us suppose we have a function that calculates distances using latitudes and longitudes of two places on the earth. So this is our helper function. So what we'll be doing is we are also generating a pandas data frame which has random coordinates of many different places for testing our data. So then what we do is we first generate the distances using a for loop. What we'll be doing here is we'll be comparing using for loop and then without using a for loop using vectorization. So in this case we are using a for loop to calculate distances. Just notice here how many times are we calling the function here. The calculate distance function is being called multiple times inside this for loop. So whatever is the length of that data frame, the function is being called that many number of times. But if we use vectorization, we need to call the function only once, and the operation gets performed on the entire array all at once. And then when we put all those things inside the chart, just notice the difference here. The green one is for loop, and the yellow one is for vectorization. So there's a tremendous amount of difference in the time taken for computing those things. So that is where things like vectorization comes out to be handy. One more ingredient of a scientific computing ecosystem is specialized and domain-specific libraries such as scikit-learn for machine learning or statistics or something like that. We have stats models as well for statistical analysis and different kinds of numeric and scientific computings. Now, we talked about the ingredients of an ideal scientific computing ecosystem, and there are many libraries and frameworks coming out these days in recent years. There is a shift towards web-based computing, and things like TensorFlow.js or stdlib, Math.js or D3.js, Plotly.js, you might have heard some of these. So these are the key players in this kind of environments. Now, what really is exciting about this point of time is that we are on the cusp of a burgeoning ecosystem for a web-based scientific computation environment, an ecosystem which will power and supercharge web-based applications of the future. And one such key player which is striving to make that difference is stdlib, which is a standard library for JavaScript and Node.js. It provides a common foundation with standardized APIs atop which others can build domain-specific packages. Let's revisit the ingredient list that we saw earlier. We talked about syntactical niceties. Similar to how R has those pipeline operators, stdlib comes along with fancy indexing, just like we have in Python. So this fancy indexing that works in JavaScript, similar to that Python thing. So what we are doing is we import the array to fancy function from stdlib, initialize the array, and then we retrieve the slices, assign the slices, and then modify the array. One more such thing is BLAS bindings, which are basically linear algebra subprograms. So what we are doing here is, just notice, we are just importing the modules which we need. We just imported DAXP and float64 array. So there is no need to importing the whole stdlib package. We can just use simple, smaller packages that we need, which can reduce the burden. We also have LA packs, linear algebra packs. What we do here is, we are doing here is just importing the packages that we require, performing the DLA CPI operation. So what this operation does is it copies the data elements, all data elements or only some data elements based on the inputs from one array to another. We talked about ND arrays as well. Similar to that, in stdlib we have ND array support as well. While initializing, we can give the arguments for buffer, shape, order, strides, and offsets. And based on that, we can use ND arrays in JavaScript in web browsers, similar to how you do in Python. There are some universal functions. We talked about vectorization just now. Similar to that vectorization in stdlib, what we can do is we first importing the ABS function. We import an array, and what we do here is we have this array, and instead of computing the absolute of each element one by one using a for loop, what we're doing is we just call the function once, and the operation gets worked on the entire array all at once. It also has a read-eval print loop environment, so which comes up with customizable themes and syntax highlighting and more such features. So you can play around with this REPL as well. This particular example demonstrates the famous PageRank algorithm which Google uses. So what happens is, at a high level, first I just want to bring your attention to the packages that we are importing here. These might seem a bit lot, but that's actually an advantage because we are just importing all those packages that we need rather than importing the whole stdlib library, thus decreasing bundle sizes. And all these things can be, executed only with the help of stdlib functionality. So, no need to import this library and this library and this library. stdlib can be your one-stop shop for whole numeric and scientific computing. Talking about computing on web browsers, how can we miss WebAssembly? So WebAssembly is a if some of you might not know, it is portable, consistent, high performance binary format for web browsers that helps us to execute code at near native speeds. It also comes up with SIMD optimization. So what SIMD optimizations help us to do is a single instruction on multiple data things. So you have a single instructions and that gets executed on multiple data elements all at once. We talked about WebAssembly. So there are also many ports of entire gaming engines getting run inside web browsers using WebAssembly. So what is this happening is this entire game engine is running inside the web browser. So no server is involved in this as well. This is using WebAssembly along with Unity's engine. Adobe Photoshop is also a good example for this. So their entire image editing software runs inside the web browsers. So this when they converted their software for the web, what they saw is they achieved up to 200% performance improvement in their model execution. So that's like near native time, real-time editing capabilities in your web browsers. Here we compare JavaScript against C and WebAssembly for the blast level routine DAXP, which multiplies a matrix which is a constant and then adds that to another matrix. So in the plot I'm showing two different WebAssembly measurements. First is labeled as WASM and second is labeled as WASM copy. So for the first WASM measurement, I'm measuring WebAssembly performance when we are already have been allocated memory inside the WebAssembly module heap. So we already have the data inside our WebAssembly memory module. So but for WASM copy, we don't have data pre-allocated inside our memory module for WebAssembly. So in WASM copy, what happens is first the entire data is copied inside the memory module for WASM, and then the computation is being done as expected. So WASM copy performs a bit lesser efficient as compared to WASM. A few more efforts for numeric and scientific computing on the web have been made by Pyodide. What Pyodide does, as stdlib helps you to run JavaScript for numeric and scientific computing on web, with Pyodide you can use Python over the web. So all your NumPy or those functionalities can be used inside your web browsers. Similarly, WebR can be used to compile R and use R operations inside the web browsers. But you might ask, so if it's possible to run Python inside web browsers, then directly why shouldn't we use NumPy or SciPy? Why to go for stdlib and why to go for JavaScript? While this is possible, doing so comes with significant disadvantages. So based on these charts, we can clearly see the differences in loading time. This is what Pyodide takes, Pyodide with NumPy, and this is what stdlib takes. That's like exponential difference. Similarly, in performing multiple operations as well based on speed, there also standard lib either outperforms or is at par with NumPy. So there have been multiple efforts such as WebAI, where you can run entire entire AI applications on the web using Chrome, WebNN, and WebGPU as well. So with WebGPU, you can use GPUs inside the web browser, so no need to use clients, use GPUs in cloud-based environments. So finishing my talk, if you really want to get involved in standard lib, you can just scan this QR codes. This is the link for standard lib's repository, blog, and the GSOC page. Thank you.
Thank you, Mr.